All right, so picture this. It's a clear night, you're gazing up at the stars.
Beautiful, right?
Yeah, totally. Except, here's the thing.
What's that?
What we see, all those twinkling stars, it's just a tiny little piece of the whole picture.
It's true. The universe is full of
Oh,
secrets.
absolutely. We're talking about the invisible universe, the stuff we can't see, dark matter, dark energy.
Forces that are shaping the cosmos as we speak.
Right. And that's what we're diving into today. We've got a bunch of really cool research articles and studies to guide us.
Sounds like a fascinating deep dive.
It is. So, first things first,
Lay it on me.
what exactly is dark matter? It's like this, this mysterious stuff, right?
It's like a cosmic phantom, It doesn't emit light, it doesn't absorb light, doesn't reflect light.
So we can't see it.
Nope, not directly. That's what makes it so tricky.
But if we can't see it, how do we even know it's there?
Well, it's all about gravity. Dark matter interacts with the universe mainly through its gravitational pull.
So it's like it's there, lurking in the shadows, but we can feel its effects.
Exactly. And get this, scientists estimate that dark matter makes up a whopping 27% of the universe.
27%, that's insane.
It's mind-boggling. It really puts things into perspective, doesn't it?
It does. But let's get into the specifics. How do we actually detect this dark matter?
Okay, so imagine a merry-go-round.
Classic.
Right. You know how the horses on the outer edge have to move faster to keep up?
Yeah, makes sense.
Well, the same idea applies to stars and galaxies. But here's the thing.
What's that?
The stars on the outer edges of galaxies are moving way faster than they should based on the visible matter we see.
Wait, so something's making them spin faster.
Exactly. It's like there's this invisible hand, this extra mass giving them an extra push. That's dark matter at work.
Wow. That's pretty convincing evidence right there.
It is, but there's more. You see, massive objects, like galaxies, they actually warp the fabric of space.
Warp space. I mean, I kind of remember that from, physics class.
Yeah, think of it like a bowling ball on a trampoline.
Okay, starting to get the picture.
The bowling ball creates a dip, right? And if you roll a marble past it, the marble's path will bend.
Cues the curve, yeah.
That's gravitational lensing. Light bends around massive objects, and when we observe distant galaxies, we see more bending than we should if only visible matter was present.
So that extra bending is like the fingerprint of dark matter.
You got it. And there's one more piece of evidence. The cosmic microwave background radiation.
That's the afterglow of the Big Bang, right?
Yes. And this afterglow has these subtle patterns that, well, they just don't make sense unless we factor in dark matter.
Okay, so we've got, how do we know it's there? But what about the big question?
The million-dollar question.
What dark matter? Like, what's it made of?
Well, that's what's keeping scientists up at night. There are a lot of theories.
Like what?
One idea is WIMPs, weakly interacting massive particles.
WIMPs, okay.
They're hypothetical particles that, well, they'd be pretty heavy but barely interact with normal matter.
Sort of like ghosts passing right through us.
Yeah. And then there are axions. These are even later hypothetical particles.
So lots of possibilities, but no definitive answer yet.
Right. And, there are even alternative theories that say maybe we don't need dark matter at all.
Wait, what?
Yeah. MOND, or modified Newtonian dynamics, suggests that maybe gravity works differently at very large scales.
So dark matter might not even be matter at all.
Exactly. It could be that our understanding of gravity is incomplete.
Mind blown. Okay, well, this is getting deep, but we've got another big player in this cosmic drama. Dark energy.
Ah, yes. Dark energy, the force that's accelerating the expansion of the universe.
Hold on, back up. The universe is expanding.
It is. And it's not just expanding, it's speeding up, like hitting the gas pedal.
Whoa, hold on. So everything is moving further and further apart at an increasing rate.
You got it. And that's where dark energy comes in. It's the mysterious force driving this acceleration.
But how do we know it's even there? I mean, it's invisible, right?
Right, but we can observe its effects. One way is through supernovae, exploding stars.
Those are pretty bright.
Incredibly bright. And by studying distant supernovae, scientists realized that the universe's expansion was not slowing down as expected, but speeding up.
So that means something must be pushing it, right?
Exactly. And that something is dark energy. And then there's, the large-scale structure of the universe.
What do you mean by that?
The distribution of galaxies.
Yeah.
The way they're clustered and spread out. It all points to the influence of dark energy.
And remember the cosmic microwave background? Those patterns provide even more evidence for dark energy.
It all fits together. And what's really fascinating is how dark matter and dark energy work together in a way.
How so?
Think of it like a cosmic dance. Dark matter acts like the scaffolding of the universe. It's what allowed galaxies to form in the first place, drawing matter together through gravity.
Okay, so dark matter builds things up.
Exactly. While dark energy is like this expansive force pushing everything apart.
So like a cosmic tug of war.
You could say that, and this tug of war determines the fate of the universe.
So what's going to happen? What's the grand finale?
Well, no one knows for sure, but there are some theories, some possible scenarios. One is the big freeze.
That doesn't sound too good.
It's not the most exciting ending. The universe just keeps expanding forever, getting colder and darker. Everything spreads out until, well, it's just a vast empty space.
Bummer. Are there any other options?
There's the big rip, which is a lot more dramatic.
Well, tell me more.
In this scenario, dark energy gets stronger over time. Eventually, it gets so strong that it overpowers gravity.
And then what?
Everything gets ripped apart. Galaxies, stars, planets, even atoms themselves. The universe just dissolves.
Yikes. Anything a little less, catastrophic.
Well, there's the big crunch. In this scenario, gravity wins the tug of war. Dark energy weakens or reverses, and the universe stops expanding.
So what happens then?
It all collapses back in on itself, a reverse Big Bang.
Okay, so those are our options. Eternal darkness, total destruction, or cosmic rewind.
Yep, those are the main contenders. But the truth is, we're still in the early stages of understanding all this.
It sounds like studying dark matter and dark energy is pretty challenging.
Yeah. Oh, it definitely is. We can't see them directly, so scientists have to get creative.
Like what?
They're building these incredibly sensitive particle detectors buried deep underground, hoping to catch a glimpse of dark matter particles.
And new telescopes, like the Euclid telescope, will help us map the distribution of dark matter and study dark energy's effects on the universe. It's like we're trying to put together a puzzle with most of the pieces missing.
Exactly. But every new discovery brings us closer to understanding the true nature of the universe. And who knows what other mysteries are out there?
Like what?
I mean, what if dark matter forms its own structures? Dark stars, dark galaxies, things we can't even imagine yet.
Wow. It's incredible to think that we're just scratching the surface of what's really out there.
Absolutely.
So we've journeyed into the invisible universe today. We've talked about the mysteries of dark matter and dark energy, these forces that are shaping the cosmos in ways we're just beginning to grasp.
It really makes you think, doesn't it?
It does. And, it reminds us that there's still so much to discover, so much we don't know. What other mysteries are hidden in the darkness? That's something to think about. Thanks for joining us on this deep dive.
My pleasure.
Until next time.
See you then.